All right, so we're talking about the definite integral and about how to define the definite integral and now let's look at some properties about the definite integral. First off, the property is if you have an integration from a to b fx dx and then it gonna equals negative integration from b to a fx dx. About this property, guys, you can think about it into this. When we set up this integral, we always assume that a is less than b. Okay, so remember, assume fx is a positive function. Okay, and then this definite integral stands for the area under the curve, right? Okay. But right now, if you're doing the interchange about a starting index and ending index here, actually, do you agree that when you doing the partition, do you see that the partition number actually are all negative if we do it in this way, right? It's kind of like something like this, right? If you do, let's see, from 0 to 4, right? You do this partition, I don't know, 1, 2, maybe 3 here. And you can see that each weights, it is a positive. You see that, right? Because you have 1 minus 0, that's the weights for the first part, 2 minus 1, 3 minus 2, 4 minus 3. But if you do the reverse, from 4 to 0, guys, if you do this partition, 3, 2, 1, do you see that 3 minus 4 is gonna give you a negative weights? So that's why this gonna generate a negative. Okay, so you can think about it into that way. The second property is called the zero weights integral property. Okay, so I try to draw the graph so that you can understand better. So assume this is my function here. This is the notation a here. And if I do the integration from a to a fx dx, do you agree that there actually the area for this part actually it's 0, right? Because it's just a single line, right? There is no area get involved. So this is what we call a zero weights integral. If you start and the n index are the same, then 0. And later on, guys, when we talk about the fundamental theorem of calculus, which is in 5.4, you use that theorem to evaluate this. It's super clear, okay? But this is just a way to think about this. Now, there are, let's see, 5 more, okay? So this is called the constant multiple property for an integral. It says like this. If you have an integral from a to b, inside it's k times fx dx. K is a constant. You can always pull the constant out, okay? And then k times integral from a to b fx dx here. And if you look at the graph, you can think about it into this way. Assume if we have k equals 2, so integration from a to b to fx dx, this is the area under the curve, okay? And do you see that if we split those two out, and this is gonna be the original area under 1fx, right? So if you double it, do you see that you get the area under this part? So this is just a visualized explanation for the constant multiple property for the integral. This one, the sum property here, it says like this. If we have the integration from a to b fx gx dx, we can split them into two integrals. From a to b fx dx plus from a to b gx dx. How do you realize that? Well, you think about this, guys. The area under fx gx is here, right? And it can be calculated by the area under fx plus the area under gx. Again, guys, think about it. There are some overlap between fx and gx. So when you add the areas up, it will become the area under this curve. So this is the the sum property. And there is number 5. Let's see. This is called the additive property. It says like this. If we have an integral from a to b fx dx, assume this is our fx here, okay? And do you agree that the area under this curve equals the area of this part plus the area of this part, right? And how do we describe the area from a to c? Well, definite integral from a to c fx dx. How do you describe the area from c to b? Integral from c to b fx dx, right? So as you can see that this is what we call the additivity. All right, so now let's have 2 more properties. Erase this part. Let's see. Number 6 is pretty straightforward. So it says like this, okay? So if I have a function like this, well, maybe let's do something like this, okay? And then this is A, this is B, okay? This is A, this is B, this is fx, okay? And the property says like this. The integral from a to b fx dx, again, area and the curve, since we assume fx is positive, it satisfies this inequality. It must be greater or equal than b minus a times f min. In other words, the minimum of fx. Well, think about this. How do we interpret this in our graph? Do you see that this is our function? The minimum number, or the minimum value, do you see it happens at b, right? So b minus a, which is the length of this base, right, the width, times f of min, which is this part. Do you realize that? Which stands for the area of this rectangle, right? So the area under this curve, of course, it must be greater or equal than this. Okay, there's no doubt. Also, some of you might already have this. It must be less or equal than b minus a times f max, right? Now, you see that we can use a different color. The maximum of fx, it probably happens somewhere here. And then b minus a times f max, do you see that? It's the area of this bigger rectangle, right? So the area under the curve, it must be greater or equal than this and less or equal than this. So this is another property about the definite integral. Let's see. See what we have. Last one. Okay, last one is, let's see, still use a graph. Let's see if we have, this is g of x, this is f of x, okay? Let's see from a to b. Now, from the graph, we can tell that fx is greater or equal than gx from a to b. Then, correspondingly, so if we, this is what we can get. So we know that gx is less or equal than f of x. Well, in this problem, it's strictly less, right? On the interval from a to b. And then we can get that correspondingly from a to b, the integral also follow this inequality, okay? Because you can do a area compare, right? So this stands for the area and the curve gx, which is described here, and this is the area and the curve fx, which is described like this. So this, these are the 7 definite integral properties which I visualized so you can understand a little bit clear. Okay, so I'll stop here. Thank you.